Let's start with a completely empty, neutral conducting sphere of radius r. If we take a single positive charge and place it on this surface, it requires practically zero effort. There's nothing there to push back. But the moment a second positive charge tries to land on that same sphere, the situation changes. That first charge is now pushing back, creating electrostatic repulsion that we have to physically overcome. Every subsequent charge we add faces even stronger repulsion. The total mechanical effort, the work required from an outside force to overcome all this increasing resistance and pack every single charge onto the sphere, is what we call its self-energy. Here in our notes, we are looking at a sphere that has reached its final, absolute maximum charge capacity, labeled with a red capital Q. Our goal is to find the mathematical formula for the total stored potential energy, U, of this fully charged state. The self-energy of this charged object is the physical sweat equity stored inside the system. It is the direct mathematical result of the process of building it. To calculate that total effort, we have to mentally pause the charging process at a random intermediate point. We will define the current temporary amount of charge on the sphere as lowercase q. With the sphere partially charged, we bring in the next infinitesimally small packet of charge attempting to join it. We define this incoming packet as dq. At this exact frozen moment, the electric potential V at the surface of the sphere is 1 over 4 pi epsilon naught times q over r. Notice that this potential depends entirely on that temporary charge, lowercase q. Physically, this potential value represents the mathematical wall of resistance that our tiny dq charge packet must push through to successfully land on the surface. Freezing time here is crucial. Because this resistance grows with every single charge we add, we cannot calculate the total work in one big step. We have to define the rules for a single intermediate instant first. Looking at the notes, this gives the equation for incremental work, dW. The effort to push our tiny charge onto the sphere is the charge packet, dq, multiplied by the surface potential, V. Substituting the potential formula we established replaces V. This new expression shows exactly how much work, dW, it takes to add a tiny slice of charge, dq, onto a sphere that is currently holding a temporary charge of q. Now pause the video for a quick active recall task. Try to set up, but don't solve yet, the definite integral required to calculate the total work, W, going from a completely empty sphere to a completely full one. This relies on the core logic of calculus.
Integration is just the process of adding up an infinite string of these tiny dW work slices, starting from the very first spark at 0 up to maximum capacity at capital Q. Here is the correct integral setup for total work in our notes, spanning from 0 to capital Q. We pull the constants out of the integral, 4, pi, epsilon naught, and radius r, leaving a straightforward power rule integration of Q. Applying the power rule yields Q squared over 2. Evaluating at capital Q and multiplying by our constants gives the final work formula. Because work is conserved as potential energy, we lock in our final equation for self-energy, U. To quickly review the 3 core steps we took. First, identify intermediate state Q. Second, calculate work to add dq. Third, integrate for the final formula. This singular mathematical box contains the entire physical struggle of forcing billions of repelling charges into a shared, confined space.